So I'm going to be talking about software, memories, and simulated machines. My background, I work with boarded software, building tools, mainly in the Corvette, in VisiBroker, then went to the app server when there was a competition around JQE servers. And then I left boarded and I wanted to create a company around software performance analysis. I was the one that was in R&D in boarded that was called out anytime a customer had a problem. I was the one that was sent from R&D, the most presentable one, to go fix the problems. And I didn't have any tools. Well, boarded did have tools, but I didn't use them, so I decided to create my own. And then I focused really on trying to understand software behavior. I had a company for a while that did kind of tooling called J-Inspired. I don't know if you know. It doesn't matter if you don't know it. And now I have, the company is kind of renamed to Autoletics. And so the background is that I initially was focused on observation, understanding, monitoring the systems. And then I wanted to extend that to something bigger, where we focused on the bringing memory to software. So I moved from monitoring, which to do monitoring good, you have to have an adaptive agent. So I started doing a lot in adaptive technology. And then I wanted to create systems that were more self-adaptive. And that's where I came to more this kind of behavioral augmentation collective. Now the talk tonight I'm going to discuss is why would you want to simulate. Okay, so software has memory, as when we talk about memory, we talk about like a heap, but it hasn't got episodic memory. And so what I want to do is to give software, and this is what all adaptive systems have, is this ability to have a memory. Now how it actually creates memory of past behavior, of past stimulus and response to that, and what is effective is very different per system. But software itself hasn't got this memory. It will always repeat the same thing again because it's programmed. It doesn't learn from it. So if a request comes in on a web server and the database is not there, it throws an error probably back to the server. And then the next time a request comes back in, it'll probably do the same thing again. Because we don't give it the ability to remember what it did. There's no recollection of what I do. It just says, I take something, a request comes in, I do this code. But it doesn't alter its behavior all the time. The data drives the behavior, but there's not a memory driving behavior. So that's what I want to talk about. And so Gartner did a very interesting chart once. I've taken this from Gartner. I've kind of jigged it a bit. But Gartner had something where they called cognizant computing, where we started with personal computing, we moved to smartphone, we had personal clouds, and then personal agents. I tried to do something with that in terms of what we're doing with software, what we should be doing. So if we just take the kind of the more monitoring, machines that are aware of machines. So the other one's kind of like where human and the machine are working together. The machine is taking over some of our tasks. So eventually there's this personal agent. But what about if machines took over other machines' behavior? What about if machines became aware of themselves? Not in a Skynet where I'm going to wipe out all the humans, but aware as in I know what other machines do. I can feel them. Not in terms of emotional or empathy, but on an understanding of what a machine does and what that behavior is. So if you take that, we have system logging. This is how we used to look at systems. We just look at the log file. Whatever was in there was the law, even though we never test log statements. No one ever tested. I've ever was asked, has anybody ever done an assert on a log statement? No, because it's always correct. Whatever's in the log file is what's happened. So then we moved to application monitoring because we were missing something there, so we wanted to kind of have a period of windows, steps, actions. The trend in the industry is so that was the see the application. Analytics is kind of to know the application over time, so we'll be looking at statistical learning in the software analytics. This is what the current movement is. So I extended that in line with what Gartner did, and there's this B-me. So where the software is kind of like an adaptive software, it changes its behavior based on an experience and some kind of goal or policies around that. So we have system dynamics, which is kind of more emergent behavior, feedback control, which is like adaptive valves, which throttle or expand the workload based on how successful they work at that rate. and adaptive signals where they kind of try to drive other system behavior around them. And then I wanted to go past that, and I wanted something, okay, what if, you know, if you take a gamer likes to extend himself in a game World of Warcraft, and he says, I am this person in World of Warcraft, but here I'm this person, but over there I'm a superhero. Can I be something like that? So I wanted to do that for the machines. Can machines go beyond what they have? And I think they can, because machines are this kind of computational kind of organism. And what if they were able to say, I want to extend myself, I want to augment my behavior beyond my construction of my creator. So this is like the gamer in World of Warcraft. What about if machines could join a game system, and they could also be extended in there? So that's some of the context, and because it affects, so of course you need a driver. You can have this great vision, but you need something driving it. And I think there are some drivers to that today. We have this mobile Internet of Things, and that has many more small actions are happening, small interactions with systems. So we're seeing that. And what we need is we need to have better observation and measurement of that. The microservices is great where we're trying to get greater modularity, both at the runtime as well, probably as design. And we have many more small systems. It's great in that way, but when you want to see the world, you want to see it as a whole, a universe. And so from observation or from an understanding, you want to consolidate that. So you want consolidation. In some way you want to partition everything or break it up. But at the same time, you want to see it work together as a whole, all the cogs together. So you want something that consolidates them. And then, of course, there's the continuous delivery. So many more small changes to the many more small systems, which have many more small actions. We're always in the past. Every monitoring tool is in the past. So, and with this change, every time you look at a system, let's say if you're Etsy or something, we're doing a change every 15 minutes. Every time you look at a system, so today when we look at systems, we have a build-up of an expectation. We've learned something and we have an expectation. But if everything's changing every 15 minutes, there's no ability for a human to get an understanding to drive, well, at least to get a memory of something to drive understanding and prediction. So how can we get that? So we have to have some ability to kind of recall memories. We're always going to be in the past, but we don't want to be in the past in terms of a metric. We want to be in the past in terms of being able to see it, see the past. So I want to create seeing machines. So if you take the typical, and this comes up in microservices, you take probably two types of calls, and we could break them down further, but I just wanted to keep it simple because each of these slides would probably be an article in itself. So we take a service calling other services. There's a service call where we request some behavior. This is a lot, the systems out there where you just need to do this as a workflow, the procedure for this, I have to call this service, it returns some data. Sometimes it's a fire and forget or a one-way call in terms of Cobra. And other times you're kind of giving a notification. You're saying, you're not asking for it to do something, you're saying, I want you to be aware that I did this because I know this drives your behavior. And I think that's a flaw. I think this is a problem because we're doing this at design time. We're kind of creating this notification to allow machines to see the machine. But we're already deciding what it is they see and who sees it and the way they see it. And I want to create a system where machines can see machines. They're completely blind today. So it's a bit like a machine wants to talk to another machine, and I mean software machines, not like hardware machines. So if a machine wants to talk to another machine, it has to pick up the phone and go, or PC call, here I go, or here's a messaging system. It's picking up a phone call because the other machine can't see it. But what if machines could see each other? They could see the action of the other machine. They could even experience it if they want. They could recall it and take over that action, or at least sense it because they say, oh, I know what that action feels like because I've done that action myself. So there's always this debate about calls and events, and I really think that they're two sides of the same coin. That we call an event are very similar. And I think this where perception was. This is a quote from a cognitive book. I think I should have put the reference down there. But perception of the environment for humans developed was developed for us to act within an environment. We act in an environment, we see what it does in the environment, and we use that to drive future action. And perception itself is shaped by learning, memory, and expectation, and attention. And we haven't got that with software. And I want to kind of show you how action, or how calls and events are very similar. So if you take a call stack of Java or any application out there, so this is the kind of call stack: A calls B, calls C, calls D. So let's say you did a stacked up, and you got that printed out. So how can you see the events in that? Because that's a call, and it's a kind of a moment in time. It's a snapshot of what the system was doing. Well, at least one thread, or think of that as an actor in the system. Well, you can actually turn that in an event stream, because it's really A, I went into A, I began B, I began C, and I began D. So I've now turned that stack into a begin event. And of course, as the stack, let's say, when the stack changes, so we've done C and D, what happens? I end E, well, I think it was A, B, C, D. Oh, I think I just made a mistake there, that should be D. Correct that. So this is where D has ended, because of course that was at the top of the stack, so that will be the next one in the stream. And then I end C. And this is where here I am. So calls and events are very similar. They're really, I see them as the same, but that you can go from one to another. And of course that's what we do when we do Alt3C. We take a call, it goes over the network, goes over the packet, comes up, being transformed, and goes back into another flow. So we have these events, and we have this system. So what I want to do is talk a little bit about memory. So humans themselves, we wouldn't be able to operate in our world, in this environment that we are, without some kind of memory of the environment. And the memory is also in part of the structure. Like, let's say, myself, I am in some way a memory of not just of evolution, but also of my development. So if everything was changing inside of me structurally at the cellular level, I wouldn't be able to act within my environment, because I wouldn't even know if I had a hand at the time I tried to act, because I probably wouldn't even remember it. But now that I know I have a hand and I know that it does these things, I'm able to act within my environment. And we don't have software having that. Actually, if you ask software, let's say a request at the top of a stack, or a request comes in and a servlet does it, and you then ask the servlet, what did you do? Have you ever seen software tell you what it did? No. Software doesn't know what it did below. It just says, no, I'm just coming out of that frame, I'm popping off that stack, but I don't know where I went. I'm just going back and giving this there. So we want the software to have some self-awareness of what its actions are. So what is the memories that humans have? So human memory is divided up in sensory data, which is very short-term. It's like a buffer. Comes in, we tend to just put this in blocks. There's short-term memory, and then there's the long-term memory. And I want to go down this path. The implicit is more the procedural, where we get on a bike, we can remember getting on a bike, and we're not even aware that we're even recalling that memory. It's maybe automated as such. But we have this long-term memory, explicit memory, and we get down to these two main, this is kind of just tagging that people have given to these two types. And what we have is episodic memory, which is event memory. It's a memory of action in the environment. And that's also not just the action that you took, but what you were doing at that time, or how you felt, or how the environment was structured. So that's episodic memory. And semantic memory is like the facts. And you need the two of them to kind of build each other, because episodic memory doesn't restore everything. It kind of has links over there, hyperlinks over into the semantic memory to build up the concepts. And also to kind of reduce the space for episodic memory, we tend to infer some of this from the semantic memory. Sometimes we build up our dreams, so when we recall, we're never recalling like it's a film, or like we have a video recorder. We kind of recall enough of the essence of the sequence, and then we use the semantic memory to build up the rest of it, to kind of fill in the gaps. And this is why when we recall, it's never exactly correct. And unfortunately, when humans do recall, they in fact write back their memory into the system. So the more you remember something, the more it gets deviated from the original experience itself. So we've seen this in a lot of films. You know, there's a lot of films that looked at machines, or the ability to go back in time, or to remember experiences. This one is more interesting. It's The Strange Days, and this is where people wanted to experience another person's a bit like what someone said here today, GoPro, where you have a camera on a person's head and you feel their experience just before they died. I think it was like a snuff movie where people would just have a recording of the last 5 minutes of his life and then you kind of lived it and you felt it. Wasn't probably nice. But you know, Vanilla Sky, there's a little bit of that too. Of course, he was caught in the dream. So we've always kind of, and in fact, dreams evolve, they say. Dreams are involved to prime our responses to the next day, to increase our likelihood of better survival. So in fact, we remember dreams, not just because they give us a good feeling, but because they also ability to train the system to respond the next day in those events. So we might imagine some kind of polar bear chasing us. Of course, you'd want to be up to no polar, it wouldn't probably be useful up there, but you'd have to have an experience of something, and then you will recall that, and then the next day you wouldn't probably freeze. You would hope you wouldn't freeze, and your body would be primed to that. So in fact, the dreams themselves use the cognitive system, the mind. They start to alter the mind and to prime response the next day. But when do we ever have software? We kind of do a little bit with machine learning, where you create a model from data, and then you give it to the machine learning, and that drives the machine learning's responses. So what instead of just applying machine learning to humans, we apply machine learning to machines? A little bit of time for, so time, one interesting thing is that, well, they don't know for sure, of course, because animals can communicate with us, but they believe humans are the only ones that are able to go back in time and imagine. So in our dreams or in our thought process, we're able to relive these experiences. And that seems something very unique to humans, that we're able to go that and in fact feel it, and time is discarded. So the past becomes the now. And I think that's what we also have to do with time. We have to not see time anymore, not have our system so time dependent. And of course you probably know this quote from The Matrix. So do not try to bend the spoon, that's impossible. Instead only try to realize the truth, there's no spoon. So we don't have to see time. We just live in the now, but the now can be a past memory. It could even be a future. You could try to give it some memory to prime its response to a future event. Okay, so this is probably a good time to, I'm only probably about 30% through these slides, but I don't want to lose your interest. You're going to say, is this a vision that's never going to happen? You know, how are we ever going to get a machine to see another machine? So I'm initially going to start with a simple demo, then we'll go back to some slides, and then we'll do the real Big Bang. So first of all, what I want to show you is, pretty much most people probably know Cassandra, the NoSQL database. And I'm going to show Cassandra instrumented with an agent. And I'm going to project its image of its behavior, its execution behavior, over into another JVM. And in that JVM, I'm going to connect a console, a monitoring tool that is completely unaware that it's looking at a JVM that's not Cassandra, but it thinks it looks like Cassandra. I need to show you that there is the ability to take a machine's behavior and project it over. So that's the first thing I want to do is, how do if memory is about this projection of action over and across time and space. So across space is into another JVM. Across time is, maybe the JVM is not there. Maybe we stream it into our file system and then we replay it. So I'm going to bring up Cassandra. Hopefully this works. So Cassandra is instrumented with an agent. I should start up the simulation first. So I'm going to start up the simulation just to show it there. Move the data. So I'm going to start up with defaults. This I think is the 1%. And I'm going to now, so there's a similar, just to show, so I'm going to connect the console. So this is a monitoring console that I built a product for JVM monitoring. And it's connected to the SIM server. This is the local host here. You can see the SIMs. And there's nothing in there. There's no behavior. It's connected, it's monitoring, but the machine's not doing anything. Because the machine is a simulation. It's a JVM that says, I observe, and then I replay it in the JVM. I make that machine be here, be in the now, in terms of the machine itself. So I'm going to get Cassandra, and Cassandra will run now. And Cassandra will project its image over into Sims. And so you can see now that there's behavior coming up here. I'll just do a refresh, and there is probes now. This is methods, Java code in the simulation. And this is the simulation here. These are threads that are running. This is what they're doing, and I can click on something, but it's just only started up. I'll wait for something. And this is in fact the Cassandra itself. So this is the real Cassandra application that's running, and this is the simulation. Now, I've got to do a stress test. It'll put a bit of workload on it. And you can see that Cassandra's now is saying that we're sending, well, at least Cassandra's doing this amount of probes. 1 million methods are being measured a second, at least in that build up there. We'll probably keep going. And you can see the threads coming up there. I'll do a refresh a little bit. And we can see the system is alive. But we can also go into the simulation. And we can see it's also doing, and the threads are there. And I can click on one of these. Let me click this one here. And I can even monitor that. And this is actually telling me the threads that are calling this. So this is the kind of all the threads doing, this is the green is the count. Don't worry about the graphics, it's just believe me that it's, the monitoring tool is monitoring the JVM in terms of threads, in terms of, this is all the methods that are being executed every second, they change, and this is the table. So we can see that the simulation, or at least this tool, believes it's looking at a Cassandra system. But of course, Cassandra, this is not Cassandra. I'll just stop the stress test. I'll shut down the real Cassandra, and you'll see that this one will say it's not available anymore. But the simulation is. And if I start up this Cassandra, the simulation will be there. But let's stop the simulation. So we can see now that I can project the machine's behavior over into the JVM. And if you did a thread dump, you will see all the threads that would have been in Cassandra. In fact, the machine takes over and says, I am Cassandra. And I will create, if there's a thread in that other JVM, it will create this thread here, and it will do that code. And it will do it in the time that it's doing it in the other machine. So it's kind of like a dancer. You're looking at someone dancing and you're mimicking them. And a bit like probably a mime artist, you're not changing the world. You're just mimicking it. So if you ever see a mime artist where they clean the window, of course they're cleaning the window, we know there's no window there. But he's mimicking the behavior of cleaning the window. And that's enough for us to understand the system. But what if I wanted to see it again? So I have a little script here that's going to take a recording, because while I was doing that, I was sending over the behavior, streaming over the perception of action over. It was kind of giving light to a machine, being able to project across that time and space. I also did a recording that says, okay, save that projection, that image that's coming into the sensory of the simulation machine, and then let's play it back. So if I can play it back now, this is just a script, and what you'll see here. And remember, when the Sims was shut down, the Sims is not running, this is the simulation. And in fact, this simulation thinks it's Cassandra. So I've now created a machine that has a memory. I now have a JVM that has memory of threads, of measurements, timing, of what it executes. The behavior is there. So I can profile a machine in the past. I can see something. And let's say I had a new visualization. Let's say, you know what? I want to see, I have this memory, but I have a new cool visualization that I'd like to experiment. Wouldn't it be great to go back and take that memory and see it differently? Let's say you wanted to see it in an Oculus or some kind of virtual reality. So every time we develop some new ways of visualizing or perceiving in a machine, we can take those memories and relive them. And present them differently to the user. So if I take that memory, let's see, I'll make sure I have the right one. So I've got that. Let's see. So I'm going to do Sims. Let's go back to the Sims thing. I'm going to run up the Sims with the Matrix extension. So what I did is I wanted to kind of convince people this is kind of like a Matrix for machines. And of course, for that, to make people see the matrix, you have to create the matrix display. It has to be there. So I've actually have it, the Sims running. It's a script that runs the Sims. But this time, the Sims crate has this extension in it that says, it's called the matrix extension. I just added it into the simulation environment, or the mirroring. I could have put it into the playback, but I put it into the live environment, and then I'm going to have Cassandra start up. This is the real. Cassandra will connect to the Sims, and the matrix is there. This is kind of, and what's happened here is all those threads, and these are all the stacks. Each of these circles is a stack frame that's happening live in the sim, and it's happening in the simulation. This extension that I developed could have even been put in the application, but I put it in a simulation. But I could even take it and put it in a playback of the machine. So I now have the ability to see, and if I show you what happens, like if I put the stress test on it, I can now see the system. And in fact, I could create one where all the machines appear in this matrix. I have a universe of behavior. So what is that behavior? Probably just a little time, yeah. So let's see, and I just finished probably this. I just do one little quick demo of this, and then I finish this one, so I don't have to remember it. So I'll have to think about it now. What about in the playback? What about in the playback here? So it's probably still running. What about in the playback? I said, hey, I wish I could go back and experience that Cassandra, but in terms of this matrix display. And that's probably Cassandra's there. And this will, you can play it back in the kind of the timeline or the time lapse of Cassandra, or in fact I could say, I could go into the configuration. I could turn off an extension which makes a time sync, and then I could say, we'll play it back as fast as possible. Because with memory, you don't have to go back to the same, you can re-experience the memory as fast as possible. There's nothing that has to change, as long as your software or your code is not timed or awareness. There's not a kind of, time is the now. It doesn't, and that's it all fast, quick forward. So we don't really jump to the end and finish. So I can play like an airbag in seconds, a recording. And in that, I can expand the simulation, put something in there that can look for something in the machine. And I could output some new behavior, or could create new recording. Okay, so that's that first part.
Awesome. Part one, part two.
Part two,
coming
even better. So where am I going with this? And is to give the machine a kind of a mind, the ability to reason about other machines and the environment that they operate in. And of course, for machines to understand machine, we have to kind of, what is understanding? And we have to use our own experience as humans, and how do we understand other individuals? Some statements I have is that the function of the mind is really to guide action within the environment. We kind of already said that, where we're operating in an environment, and the mind is to guide our action within that environment. Without action, we're doing nothing. And so there's always this duality in terms of the mind and the brain, some people say, and then the body. So there's a couple in between what the action is, so what the body parts are, and the mind. And I don't think they're really very different. And a lot of the time what's happening in the body is really the feeling what's going on in the mind. There's some kind of representation there. At least that's what we think there is. And we see this in, I'll just go a little bit ahead, because we have these mirror neurons in the brain, and it's been, at least the research shows that. It's been done in monkeys, at least initially. And that is where, so when a monkey performs an action, they've been able to monitor which particular neurons fire during that. And the same monkey looking at another monkey doing a similar action will fire the similar neurons. At least the mechanism seems very similar, the pattern of behavior. So the belief is that humans, in understanding other humans, have a kind of a little simulation of the other person within the mind. And to do that, we have to understand that feeling of the action that that person does. They say that you can't understand someone else until you walk in their shoes, but it's also about action. So to really truly understand someone else in performing an action, in fact, you have to previously perform that action. And so, and there's one phrase common that I think probably most of you are familiar with is all doing is knowing and all knowing is doing. So there's this coupling between the doing of it and the understanding or the knowing of it. Now, in cybernetics, there is a kind of the good regulator theorem, and that's every good regulator of a system must be a model of that system, and as nearly as complex as the system it's trying to regulate. So if we look at monitoring systems, you know, software has threads, has scopes or execution of calls, call other calls. There's this kind of nesting of scopes of frames, stack frames, you could say. And most programming languages have that. They have a thread, they have stack frames. Each stack frame represents a call scope. And they do a lot of this, you know, the tree of life, where there's a pattern of behavior across many different call sites. So we need software to be able to see that. But today what we do with monitoring tools is we send metrics over. We send little blips. And that's a counter of something. We don't know what it is, but we don't know how the mapping went from action to this blip that comes over as a number. It's not action anymore. We have sent, here's a value, and I've given it this name. But where is the action? I can't see the motion of the software anymore. Someone has taken that and said, every time I do this code, I might count something, and then that count goes over there. And then someone sees a count or a number assigned to a name, but doesn't really see the action anymore. He just sees what's happened in 1 second, or maybe what's happened in 15 minutes. We really haven't got monitoring systems that monitor other machines by taking over the machine's behavior. So what if a machine, if a machine was to be truly a good regulator of another machine, in fact the machine would have to be the machine itself. It would have to have the same behavior. It would have to do the same actions as the other person. It might not have the same impact in the environment, so it could be immutable. You know, like I could simulate it, I could mimic it. And you know, as a dancer when I was young, so I've always known where, you know, when you're learning a new technique, there's a period where you're frustrated as you try to copy the dance teacher. And then there's a moment where it just clicks, where you feel you've got that movement, where you know you're doing the movement that you were meant to copy. But prior to that, there was a kind of a mimicry, you know, there's this, but it wasn't right. And then there's that moment where you feel that you even you've become the teacher. How many of you looked at a film and you kind of looked at an actor and you kind of like, you sense that you could be that actor and be that actor acting like someone else. Sometimes you can even feel that you're Michael Fassbender or something, but you're probably not looking like him, but you feel like, oh, I think I feel I could be him. But just get it. So does that sense? And of course it's a projection of what we're trying to do. We want to feel like that. We want to say, oh, by mimicking that person, I become that person. Yeah? And that's what an actor is, isn't he? He's taking what he sees, what's written down in the script, and then he's projecting, he's making those actions play out, and at that moment he's simulating that person in his mind. And the better that is, the more realistic it is to us. So we want motion. So I went looking for, okay, so if I'm going to describe machines, if I'm going to get a machine to understand a machine, I need a language for them to communicate. I need to have some kind of framework and understanding of what that person is doing, or what that other machine is doing. So I went looking for, how do we describe human behavior? Because I'm already simulating mine, so now I have to understand, if humans understand other humans, they must have some kind of language. There must be people who, therapists that go and understand human behavior. Maybe a machine needs a similar framework or language to do that. So I went looking for something. And one is this is a critical theory. I thought it was like I'm out of time. Okay, so I came across this one, and there's this. So there's one here where we have agent in an environment, which you could probably say an actor. Typically, an agent operates in a scene, an environment. He has an agency, which is a way of performing an action. He wants to perform an action, and then he performs an action based on some intent purpose. And then there's, of course, the agent himself has some kind of state. It has an attitude to why he's doing that. And that's called dramaticism or something like that. And then we have crime scene profiling. So I had that. I said, okay, maybe this is a language. Act, what was done. Scene, where was it done. Agent, who did it. Why did it happen. And how was it done. Then I looked at crime scene profiling. Very similar there. What crime was committed. This is, by the way, from the FBI. Crime scene profiling methodology. Where the scene happened, time the action took place. That's not addressed in this particular thing, but because they don't really concern so much about temporal, because the scene is the temporal aspect there. It's already, time is wrapped in the scene. Who the agent was, why, the motive, and the how. So, okay, I said, okay, maybe this is something that I can do. So then I said, okay, I've got this language, I need actors, and what's an actor in a machine? So what would you say an actor is in a machine? Well, has anybody got a suggestion? So a computational machine, what would you consider an actor? What does code execute on its own?
The processor.
So the processor is probably acting on behalf of something, but what we would probably, in terms of software, the processor is the hardware, and it does perform the instructions. But what's driving the instruction?
Process.
The process. But what's inside of the process? Do we have a single actor, or do we have many actors competing in a process?
Threads.
Threads. So I said, okay, maybe threads are actors. I mean, the process itself could be, it depends on, it's a bit like scaling, depends on which way you're looking at it. So I said, okay, a process, you could take a process as itself, as an actor, which is like a service, especially if a process only ever does one thing, which is like microservices. But what about if there's a process and it has everything going on? It has many different behavioral patterns. And then we have probably threads represent actors, or represent an instance of that actor. So we might have multiple instances of what the process pattern is, and they become threads, or clones, like Smith. So so I said, okay, I want to measure activity, and I was looking for something, and I live in Holland for probably about 10 years now, but my first job when I left DCU was a weighbridge system for our cement. And what happens is, a truck comes in with cement, goes over this weigh bridge, you weigh it drives in, drops its payload, comes back out, we weigh the weigh bridge, weigh the truck again. The difference is what was deposited. And that's a weigh bridge system. So it's a metering system. And I said, okay, maybe metering system, because I don't want just to measure just cement. Like if you take a washing machine washes clothes, that's an activity. But when it does that, it consumes water. In washing the clothes, there's powder being consumed, and there's also electricity. So I wanted something that just didn't measure one dimension of an activity, but multiple. So I looked at activity-based costing, and I came along and had something called activity metering. So in activity metering, you normally have some kind of probe, or you have an activity that you have to measure, and you have a probe for that. And the probe is what we also use in the weighbridge system. In terms of, if you talk, so this is the device, and then you have a meter. What's the weight on the weighbridge? In terms of washing machine, what's the water now? What's the water later? This is how much consumed. What's the electricity? So the activity consumes resources. In terms of code development, the probe is the execution of code, and when code executes, it has a counter. It could be a clock counter, it could be a CPU counter. There's something that's up to that thread itself, local to that thread. In terms of design, it's behavior. Really, activity is the behavior of the system, and the resource that it is, we tend to model that as a kind of a usage of the system. And in terms of grouping it, you want to group, there's always this grouping of activities. Data-wise, we group activities, and we produce metering. So I have a probe, code executes, the context is, or like the actor is a thread, there's a call performed. Of course, this code is just sitting there waiting to execute. The call says I need to do this, the code executes something else. In the time between it enters a method and leaves the method, a meter is changing, and that produces a metering record. I did this initially because I wanted to create a profiling system. I wanted to be able to measure a system's behavior or optimize systems. My main work outside of this, because this tends to be more research because no one's ever bought into the crazy idea, I tend to work on trading environments, optimizing trading platforms, waiting one day for people to latch onto this. But going back, we have activity, action, and actor. And we have these begin and end events. And that's a model. So that's the kind of an actor has an activity, activities generate events, the beginning and end, there's resource consumed in that, there's some kind of context, there's an environment like a process, and the coordination, which is where it's happening, the place. Of course, that's a bit hard to, when you talk about machines, you know, is the machine the place? I then also said, okay, that's great, well, how am I going to create memory? I create memory for people and for machines to see. Because it's not just useful just for the machines, it's also useful, we need to see it because we need to drive other machines, we need to make machines observers of other machines. And before we do that, we probably need to be able to see it itself. So I turned to something like, how do people create memory? How is memory stored in the brain, episodic memory? It's actually very hard, no one still hasn't come up with a way it's stored. So I looked at films because that's what we think about video recording. When we think about an experience, we went and looked at a movie, we have that experience. And in the films, you have frames, you have clips, which tend to be a run of emotion. You have an act, typically the director in the script has acts or scenes. The scenes are probably tied to temporal and a location. They tend to be there. There's a setting, state, and then there's behavior and change. Actors perform behavior within a scene. There's a change also to the actors, but also change to the state of the environment or the state of some object or the state of the actor himself. In terms of when we map this to kind of a machine or kind of more technology, this would be kind of like a recording. The snapshot would be where we take a picture, a photograph of a frame. Clips where we should probably take a ROM. I couldn't go up with a technical name for that. When we look at systems tend to operate in phases. We know systems have these kind of phases like startup, shutdown. They're very simple systems, but a lot of execution add phases to this, to the behavior of the system. Time is the kind of more the scene, the environment, actor. At least that's where, and I'm not talking about actors as in actor, but actors in the kind of context, activity, and events. So I said, okay, that's great. That's a memory. That's what I need. I'm on something. I'm going to jump a little bit ahead on this, the cloud, because I don't think we want to really have to move ahead. So thinking about machines, thinking about movies, thinking about all of this, and I came up with the matrix. So this is kind of the presentation really to tell you how I got to where I am now. Is that I said, okay, well, users are out there, they're doing actions. Machines are now becoming a proxy for human behavior. We don't see human behavior anymore. We see devices interacting, and people are driving interactions within organizations via the machine. So if I want to see human behavior in the future, I have to see the machine behaving in proxy for the actor. So where we click on things, activities on devices, activities on computers, to monitor users, we don't monitor in the old way of looking at employees and behaving well. We look at what the machine is doing on behalf of the user. So I said, okay, let's have machines, have them simulate into a matrix environment. Because I want to see the world, I want to see it all together. I did that, proved it, and it has some benefits. So one is that, so we have an infrastructure, developers want to see understanding, we want to see it in the environment, but to production people, when you tell them you're going to give them this level of high HD, high definition recording, it scares them. It's like, where's this going? Where's all of this kind of behavior being projected over? And, I don't want to let people see what's happening here. You can't get into this environment because this is production. It's like it's connecting, operations are close it off. This is a little bit before DevOps. But developers really want to see the richness of what's happening here. Today, when you write a piece of code and you go onto that line of code, you don't have something telling you, just before you change the code, how many times is this executing every second this moment, as seconds go by? There's nothing in the IntelliJ editor saying, well, you know what, don't make this slow because we do this amount of times every day or every second. Or how many threads are doing this particular work at this moment. So there's no feedback. The developers haven't got this richness. And I wanted to give it to them, but operations won't let me get in here. So what I said is, okay, put this agent in, project the environment over into the simulation, and get the developers to see the simulation. And because the simulation is so realistic, they feel they're in production. A benefit too is infrastructure can change, so machines can come up and down, but the simulation is already running. And we've seen this with Cassandra. So when I shut down the Cassandra, the simulation was still running. So you kind of take elasticity in the cloud. What happens when you've no cloud instances running? What does your monitoring tool say? Is it because you can't see? Is it because simply something crashed? Or is it because you didn't need any instances? So when you monitor a system, you need a kind of a placeholder saying there is monitoring in the system, or the application is alive, but the application is separated from the body. So it's a bit like Buddhism, where we have this consciousness and the body is that realization. So the body is the instances in the cloud, but the mind or the consciousness we believe exists always. So applications is a kind of a concept that's not tied to a process. We say there's an application, and then there could be 10 instances or 10 processes or 100, or could be none. But the application would still exist, wouldn't it? But even if there was no instances. So we need this ability to say, it is there, but it's not there. Okay? That's very Buddhism. So it's always there. Even when, and so what I created is, the simulation is there. And the simulation says, well, there is no one here, but I'm here. I'm the consciousness. So I said, okay, that's great. So I can now isolate the environment, and I always have an environment even when there's no environment, there's no infrastructure. But the application is still there. I can even say, where were you a few minutes ago? Because the application is still there, but not the body parts. And when the body parts come online, they connect to the simulation and say, I'm present, I am here. So that's great. So, okay, that's good. Now I've got this whole isolation. But, you know, people, and this is where we also come to microservices, you always want to extend the system. You know, people say, oh, we need security in the system. We need auditing. We need business analytics. We need service level management. How do we get that into this system? So someone has to change the code. But what if, in the mirroring, in this other environment, we made the changes there? What if we didn't want to always change this code that's in production that's performing? What about if we take like the kind of AOP, aspect-oriented programming, where we have this cross-cutting concern, but we cross-cut it here, in the simulation. We can cross-cut it into a different space. So normally we would weave code in here that says, do auditing, do business analytics, and we'd have to change that environment. What if this environment didn't change, but it always protected itself? And in this environment we said, you're the simulation, and you are this application, but you don't have the data, you mimic it. And every time you mimic it, I extend that mirror, you know, I have met that mirror, or the mirroring, and I add in my security. I add in these analytics. And of course, if I'm going over to another space, it could also be another time. So maybe I don't even have this application running at this time. Maybe I do all of this processing at night. So my second job was billing engines. I used to work on GSM billing engines. So we also had to run, we had to process all call detail records, CDRs at night, and then create billing. So this same thing is here, that we could actually take the behavior, relive the behavior, but perform it there. So someone says, what if we added in logging into the system? We say, well, we can go back, we can take the memory, relive the memory, put the logging in that we didn't have at that time. So every time you extend the system, you have a memory where you can go back and test it in the application itself, or the simulation. And of course, if you write it good enough, you can always move your extensions between the simulation and the infrastructure. And that's what in fact, the profiling tool I created. What I wanted is, some of our customers they needed more data collected, but I didn't want these applications, the heap size was pretty fixed. And I had a little bit of tolerance room. I hadn't got enough to put in this new extension in that needed to collect data. But what I did is, I put the extension in here, in the cases where I hadn't got the threshold. And the code never changed. The code could have been running here, or could have been running there, and it didn't have an awareness that it was in a memory, or in a simulation. So what does that look like? So I was like, how do I show people what a kind of an ability to augment behavior in another? We kind of seen a little bit with the matrix, where I showed in the simulation I created this matrix thing. So what I wanted to show something that's probably less techy is the kind of, so I have this client application, and I'm just going to run it up first of all just to show you what it is. Maybe just run it like that. So I've got this application. This is a real application. It's trying to connect to the sim, so I haven't run it yet. And this is what it does. And it can run multiple ones. So this is a ball moving around. We've all seen this in programming. And I wanted to take this little window and say, I'm going to project this over into a simulation. I'm going to see it differently over in a simulation. Because we all see, we all believe that we understand something else, but of course our understanding is driven by what we have inside ourselves. It's our perception of what the person is doing. So that's the application, but what if I'm going to run up the simulation, and I put this extension in the simulation, and I create a little window of what the desktop is. And I said, I watch for machines that are like canvas apps. And I watch for a ball moving around. Now it's not watching the pixels, it's watching for a machine that's moving a ball that is rendered in terms of a circle. But in fact the code itself here is saying, I see movement of balls. Of a ball, of a piece of code that says move X or Y, X, Y. But I don't know what how that rendering looks like. So let's go back to the application and run it up. And we see that the ball is moving there, but in the simulation, it's moving over there too. And it's, it looks a bit slower, but that's because this is the window. This is representing the whole desktop, and this is representing this. So okay, now I have the simulation. It's kind of seeing that ball, but even though it's not seeing it in the exact same way it's rendered here, it's not seeing the rendering of pixels. It's actually seeing the rendering of actions, which are just rendered by this tool in terms of that movement, but I render it differently here. But what if I wanted to create multiple machines running and in the same window? So let's do a few of them. And then we can see them here. And then in the simulation, I said, okay, what if I augmented to give an awareness of the two machines together? That are not, each of these applications are here running. You can see them there. But they're unaware of each other. But the collective, the kind of simulation can see these machines. And you could have this new kind of form of collective intelligence. So one of that would be, what happens when we collide? So I'm going to bring them over to try and encourage them to collide. And you can see now they're connected. So that's kind of like where two guys met. And I'm aware that these people have a past experience. They bang into each other. And the simulation's aware of it. Of course, they don't know themselves. But the simulation is. And I can bring up another one. And then see, and of course I can always try to encourage it and hope for, and eventually they might connect, bang, bang, and now, they're kind of flashing, might use it right now. It goes orange when I'm nearly getting there, and hopefully they'll get, try to encourage it a little bit. I could be encouraging for a while. Here we go, go. Here. Okay, so now they're all joined up. So that's the application. So this is kind of a collective intelligence. So the simulation could be something bigger than each individual service itself. And of course, there's always, so I'm going to bring the simulation down. But once I have the simulation, I can always play back the recording. So this is a recording that says, hey, that streaming of sensory data that came over, or actions that was perceived by the simulation has been recorded, and you can recreate that environment. So I think we got this machine running, didn't we? And then we killed it, and then I started up. I think there was one machine running for a while, and then I shut it down. And go right up there. I think that was when I was moving the window. Remember, I moved the windows around just to show, and I think now I kill them, and then other ones come on. Okay, so I can now augment the simulation. We'll come back to that. Come on, die. I should have done that quick. Okay, there's that. And it's going to, the other few will come on shortly. So, but the augmentation is now in the, I'll just see, wait for the other one to come up, and then we'll see, come back. And it's reliving it, so that's the way it was protected. So it's reliving that experience, the machines. But it's really living in the simulation and in terms of the augmentation. So the augmentation can happen across space and time. Okay, so why is that really good? So what can we do with that once we have that? I'll come back to ping and pong if I have it. Oh no, okay, I think I'll stick with this now. So if we were to create the old game ping and pong where the ball goes across. So if you were to create a human way of understanding another person, what you would do is you'd have a piece of code that says, I throw a ball, and the other guy takes the ball that comes over and throws it back. Yeah, that's what ping and pong. At least something comes over, I receive it, I throw it back at you, you get it, you throw it back at me. Okay, so I've got that. So and I have a piece of code that's ping, and I have pong, and they can do, I'm pinging, I'm ponging, this is my action. But how can I get ping and pong to see the other doing their action? How do we do that in terms of the human mind? Well, I need simulation inside of the application. So here we've had simulation up to now, it's been in this other kind of dumbed down container, a memory system. But it hasn't been an actual application itself. But what if a service, every service had a little memory, a little simulation of all the services that were existing in its environment? So what I've done here in the piece of code is I've got this game here, and I've got a game in another process, but I've embedded the sims, the simulation in here, and a simulation in here. So this is this GVM I've been running up the sims. What I've done is I've actually embedded this simulation in here, and the simulation in here. And then when P performs an action that's metered or measured, the simulation says I will project it over into my sims, wherever that is, I'm projecting it outwards. And in this other process, where there's really an application, it actually has an ability to perceive its environment, which is in fact a simulation. And the simulation says, I am ping, and I am doing ping. And then when I see ping, because ping is ping inside a pong, ping will change the game to say ping is doing ping. And pong says, okay, so he's done it, so now I can do pong, and I'm going to do pong, and he performs the pong action, and pong is an action that's projected over into ping's environment, and ping has a simulation here that says, I perceive events from the other world, and I see that ping or pong is ponging. So now that he's ponged, I can ping. Okay? Yeah, it's okay. I get lost in that one, but that's why sometimes I try to avoid it. It's like, am I feeling up to this tonight? so what does that code look like? It can actually be, and what I want is, I don't want ping and pong to be aware of each other. So I don't want him to call. I don't want ping. So if we were to do kind of web services or any type of RPC today, when ping did ping, he would probably call to pong and say, I'm doing ping. Yeah? And then when pong did pong, he would tell ping, I do ping. Yeah? Or I do pong. Yeah? So, well, I don't want that. I don't want that coupling. I want this to be, I want them not to be aware of what is driving them. I want them to have the perception of there is something happening, but I didn't want the code to be it. So I created a little demo to show how simulation could actually decouple the systems from even knowing there is another pong. So I have a game class, and all it does is, so ping will call ping, and ping goes in here, and what he does is, when he goes in, the state is already ping, and then he just says, I wait while the state is ping. And when pong comes in, pong is going to say, well, I wait while the state is pong. Pong won't be called until it is pong. So when the state has changed to is. So what we should have is that these threads, when they call into here, they should wait. They should be simply waiting around until someone changes this state. But the state is in two processes. This is what's interesting, because I'm going to actually have a game running. So ping, when he starts up, he's going to have a game. He says, I'm going to have a game, and I do ping. Well, I actually start the game, so I go, while true game.ping. He's going to go in there, and that's all he does. And then pong, so this is like the real microservers, the kind of ultimate microservers. And then pong, it says, okay, I'll wait till the state was, so I'm kind of like waiting for something to start up, because I'm going to start with pong initially first. He's going to wait around until the game begins. So initially we have a state of null, I'll wait around, and then as soon as that state's changed, then I know ping is kind of done ping, and then I go in and call pong. So somewhere something's going to have to change the state. But what's interesting here is that the state is in two processes. So someone's going to have to update that, synchronize that. Okay, and so I'll literally show that working. And I'm going to run up pong. And for you to see it, I'm going to, so that's Pong running. And let's go into the console. So I think I can go back to the console. So this is, because it's instrumented, measured, the code, I want to see the behavior. I can go into this JVM. And there's the JVM. It's connected to Pong, but it's waiting. Pong is waiting. He hasn't done any action yet because he's waiting for the state to say the game has begun. He's waiting for ping to do the beginning. So now I'm going to run up ping. And he's going to be another process. So let's run up ping. And he's the one that kicks off the game. And then we're going to have some activity here. They'll just try to connect to each other. I think there's a little wait period and then they start warming. And then you can see suddenly ping, or in fact it's Pong, it's the Pong game doing the ping because he's receiving that projection. And there's, I'll just do refreshing that, and there's Pong. So somehow Pong is being called 500 times a second in another JVM. So I've got these JVMs that are synchronizing. Pong and ping are being called. You can see that the other one's even calling the other. So how is this working? So what I've done here is I have this little intercept that runs in the simulation. The simulation that's in fact, so there's a little bootstrap part that actually creates the simulation inside of the ping and Pong process. It says load up the sim, so actually it's using a old version, see. And it's loading up, creating a class loader, projecting, it's saying here's a simulation. I'm actually embedding it, because the simulation, I never created it to be embedded in the environment. But I said, what if I actually created the process and embedded it in the application? So that's what the bootstrap does. He bootstrap the simulation inside of each process. And then there's a little interceptor. And what this interceptor is in each simulation. And what he does is he sees actions happening in the environment. So when you go into, when P goes into the game Pong, he goes in here and he says, so this code is going to be executed every time ping and Pong do the method. And what he does is, if n equals ping, which is the name of the action I'm seeing, then I am doing ping. If n equals Pong, then I set the game state to Pong. So the precept, which is happening in the simulation of each process, is saying, I've just seen ping, do ping. So I'm going to change the game state to ping. And in the other environment, he's going to see the projection of an event coming into the environment. He says, hey, I've just seen Pong do Pong, so I'm going to change the game state to Pong, which will bring out of each Pong will then, in terms of ping, because ping is in this loop, we have ping waiting here till Pong, ping waiting for the state to change. So when the precept or the precept here senses the environment, sees a change, it will change to him, he will come out and he of course go back in again. He will try to execute the method again. So I'm actually getting these guys to coordinate each other by simply embedding a kind of a little brain that's receiving a signal from the other guy. But I've decoupled them. There's no RPC call. They don't even know if they were existed at that time. So there's someone that could see me, and if they see me, they might respond in that way. Of course, if he's not there, I'll probably wait around for a long time. But that's how we look at other people's actions. We wait for their response, and then we respond accordingly. So I want to have machines to see the action of the other person in that manner, to sense it, and then to use that to drive their state. What's great about it is I'm not dictating what should be in the payload, what's in the event. Anything could be in there. These two guys are not aware. They say, we always project action, and we project some kind of state. There's always a state or a little argument associated with the instrumentation. But I don't know how it's interpreted. I've decoupled this, where RPC calls or how we design services, you're like, here's your data that you wanted, because I already know what you want. Or sometimes we don't know what you want and say, here's a load of stuff that you need. And you probably don't need it. And in fact, what you want to do is, here is me doing work, you probably want to watch me do it. And of course, there are parts where we want to call something, we want something back. That's where we know. That's where you're giving a command to a subordinate. But where people are working together, they're watching what each other do. In a jazz band, you're sensing what the other person's doing, and you're changing your instruments, or how you play the music, by that sensory. So, okay, so that's the Pong, and then we're nearly there at the end. I know it's probably a bit tired. So possibilities. I went to Microsoft, I honestly did, and I said, you know Clippy, that was not a good start. And I said, well, what about mini-me? I said, Word document, every time someone starts up Word, it crashes. What about if every process on Windows had a little process? A little mini-me that was a shadow or a projection of whatever Word or whatever application Microsoft builds was doing, and it crashed. So today we generate crash report. When the process shuts down, we suddenly have to dump everything, and we try to get a real application process core dump if we're lucky. But what about if there was always this little guide? Every time you started up a real process, there's a little mini process, and he says, I am you. And he's always running. So when you crash, he's there. So when we want to get diagnostics, we go to the mini-me, because he's not going to crash. Because he doesn't do much. He just mimics. He's not changing data environment. And he can tell us what this thing was doing just before it crashed, because he'll be like, I was here. I was doing the robot dance. So I can see that moments before. And of course, if he hasn't memory, he says, well, do you want me to show you? So this is like Jim Carrey where I do this, you know. So I can show you the last few moments that I was doing. You want me to replay it again? Okay, I'll do it again. So we have this ability. And another thing is, what about if Word went up and said, hey, mini-me, what did I do the last time? Because software today, every time it starts up, it's a rebirth. It's like, hello, is anybody out there? I'm trying to learn, I'm beginning all over again. It's a clean slate. But what if there was a mini-me that says, listen guy, don't do that again, because that didn't work out at all. Here's what you did the last time. Stop doing it. So what about if the mini-me became like in the Matrix where download the pack, I want to fly a helicopter. How do I do that? Oh, I've done that before. So software hasn't got that, so we can actually you can use it, in fact, as a kind of an external consciousness of the application. And it could download it. Every time you say, hey, mini-me, come in, take over me. Okay, no, I feel like it's all right. Oh, yeah, that didn't feel so good. Another thing is, we could decouple space and time. Say, anytime an application is running, we mirror this behavior. We don't even know what we might want to do with the behavior, but later on, or at that time it's happening, we want to do service monitoring, security, workflow. We can put it somewhere that's, and it's a kind of like a change, you know, we're taking this kind of isolation, but bringing it over. The code will still be running in the flow, so when a thread in the simulation is doing the code that's in the real application, your security will be running in the same thread. So the security code could look at the stack, but the stack is not this. It's not the real application stack. It's the simulation stack, but it would seem real, and you could put it in here. So you have this new way of not having always to change these guys, because these kind of things are more destructive to services. It's like, oh, we need this, we need it, we should have got that. Why do I have to go around changing all of these when I can just change the simulation? And what happens if I didn't have it at a time? What happens if I want to run it later? So I could actually play it offline. So anytime computing. So we should be designing systems to say, what do I have to do now? And what can I defer to another space and to another time? And we're kind of doing that with parallelism. But what about if we extended it to be, it will happen sometime, maybe, or eventually. For DevOps, you have an in-flight simulator. So we have total recall for DevOps. We can relive an experience. So you're a new recruit on the day, you go into DevOps and you're like, okay, how am I going to get, earn my keep, or how am I going to make a mark in here? And what they could do is they could put you in a kind of a monitoring console simulation. Say, listen, the last time here's the last 10 crashes that we had in production. Sit there and watch it happening unfold. And watch it like you would really see it, like it was live in production, and because you will have the motion play out. And as you're playing it out, see whether you could predict or have a sense of what the system is. So it's a bit like, I've already got a feel what the system does, so now I've got some learning, I've already trained myself, I can go into production and I already have this sense, even though I've never been in production. I can suddenly condense all of this knowledge very rapidly in a few sessions. And what about alerts? So let's say you have something happen in production and someone says, we should have generated an alert for that. Okay, let's put an alert in. How do you test alerts today? Someone says, I hope it's going to fire next time we happen that. Let's hope it doesn't happen. Most people don't test alerts, but if you could play back it, you could see whether the alert would alert. So you could say, hey, did it fire? No, it didn't. Okay, so we didn't do it right. There's something about the sensitivity of the alert. And how would it look like when the alert happens? Would it cascade? What about when you have alert systems that are cascading? There's a chain of events. What's that going to feel like if we put this alert into the system? What will that generate? We could simulate it and feel it. And we wouldn't have to construct a script. We already have the memory of the application. Another thing is, what about if the universe wasn't just Java? So I use Java because it's just a good prototyping. That's where I make my money with the profiling and the optimization. But it doesn't have to be. The simulation doesn't have to be Java. It could be any machine code, because I've already brought it down to sensing actions and events in the environment. So it could be Scala code coming in, Java, Ruby, JavaScript, Go, could all come over into this simulation. And the simulation could play it back, whatever the simulation is written in. It's written in Java in this version, but someone else could use any language. But you could bring all languages together. So microservices is about breaking everything up, optimizing the implementation to the language. Maybe there's a particular library that you like, maybe machine learning, you want to go to Python. But what about in the environment that's monitoring all of that? What about if there was only a common, single, uniform way of representation of that, and that was a simulation? And there you could write your plugins, and the plugins would work across whatever language of choice you had for the service. So break up your services, but your universe would still be the individual human behavior, or would have diversity, but the actions would be very similar. So that's just the difference between scripts. I think I'll just take a break. Is there any questions?
A couple of questions.
Yeah, just a couple of questions, and then I have a question then. So, in terms of the details of the implementation, are you actually looking at? Are you using things like kernel probes and stuff like that, or is this at a slightly higher level than that?
Yeah. So the tool that I use for the profiling is an adaptive agent. So that's where I get. It's a profiling tool that instruments method invocations. So there's one for Java, C#. I haven't got one for Node yet, but that's something that could be done. There's one problem with simulating machine or mirroring machine behavior over into another machine is overloading of behavior events. What is of interest? So the Java profiling agent has an adaptive mechanism based on thresholds and all that takes instruments 10,000 methods, but very quickly learns. I can show you in the console another time. But learns the behavior that's reasonably able to project over into another environment and narrows that down to 100, or maybe 200. There's no number. It depends on the threshold. But it figures out what your hotspots are, just like the JVM hotspot, and it kind of identifies hotspot of activity behavior, and that behavior is projected over. So you're never getting the whole JVM execution, you're getting the essence of it. Because simply the mirroring system wouldn't keep up, and if you can't keep up with it, then you're not. That does bring up a question: is what can the mirroring system keep up with? Well, the mirroring has, for every thread that's in the other environment, has a kind of a simulating thread here, and it really is like a real thread. And so when it goes into a method, it waits until the method exits. So it's not consuming CPU. It's just simply this waiting for the event to say, I pop in and out of this stack. So it simulates it to that. So the only thing you have to do is, and a probe doesn't have to be method based. So there's an API, there's a probes API up on our website, and it's up on GitHub, and that has a probe where you go begin and end, and that signals the events. That turns into the event stream based on the extensions that you have enabled, and that goes over into the environment. So all you need is an ability to say, I'm starting an activity and I'm ending an activity. But activities are always nested, so you have an activity that does tasks do operations and actions. So it's called flow, but the profiling engine or the metering engine has intelligence to figure out what to continue to measure and what to continue to instrument. So our technology will remove bytecode on the fly after it's learned the behavior of the system and said that this method is a get. It executes with no time, or it's less than a microsecond. Typically, anything less than a microsecond will not get projected over. But what I want to do is to build these other kind of client ends that project over into the simulation. And all the extensions I've built will work in the simulation, even though the language of the client will be different. Because there's a binary protocol coming over for describing machine behavior.
Yeah, just on that, have you measured the impact of the instrumentation on the system?
Well, the agent is already used in trading environments, and to get in the trading environment, you have to be fast. The slide that I had just before this, we can do, one simulation process can do 540 million events per second on the Google Cloud V32 CPU. So I think there's not many applications out there that are generating 540 million events a second. And we're able to do that. And in fact, the limit on that was the bandwidth. We had got up to 885 megabytes a second. So the limit is, and they might say, well, that means that an event is maybe 2 bytes. And that's it. So in terms of streaming, an event of entering into a method and leaving a method, each of those would be typically about 2 to 3 bytes we send over the signal. Because what happens is the simulation can already predict what's the next action. So we don't have to send a whole what I am doing. I only have to send is when I know the simulation might not predict what I am doing based on its past history. So there's kind of a statefulness between these two memories. So the simulation has event stream, but the event stream is not your very typical event stream. It's an event stream that can reconstruct itself on the fly. So it's not, you can't read events, in fact you have to reconstruct it.
So it's a call and return event stream.
Yes. That's it. And of course it's nesting here, yeah. And that's what I did at the start where I showed you the event where I said you could take a call and turn it into 2 events. Of course we also pass over some data, some metadata to give context, and we have to say which thread it is. But threads tend to be bursty, so you don't always have to send over an event which thread it is because it's in the stream, it's probably very co-located and temporal-wise. So we don't always send a thread ID, we have a kind of a bucketing system if it's like this thread is busy. When there's a bit of interleaving, then the size of the typical event stream might go up to the 5 bytes per event.
One more?
Yeah.
And you're using it, as you say, in a production trading system.
The agent, the instrumentation, yeah, the whole metering engine is using is in trading environments. And I did the simulation was because the trading environments wouldn't allow me to create memory structures that I needed to do aggregation statistical analysis. So I bring it over into the simulation and I can do more work there. I have a bigger footprint than the simulation. And also I can see across multiple processes, which is important for those monitoring. Of course, that's where I came from. That's what I can try to make some money on. But the vision was always to build the mirroring machines because I seen the potential. I said, well, okay, that kind of has helped me take an extension that normally would run in the application and bring the extension over to the simulation. I said to myself, why not do this for every application out there? Why does it have to be a monitoring profiling tool? I could extend any application. If applications can project their image over into another machine, over into a recording, and that can be played back, then people can do the same thing that I'm doing, augmenting in a different space, augmenting in a different time.
And are you sending over method parameters as well?
Yeah, it can send over. Yes, you can pick which method parameters.
So that's what you're doing for the. That's what you're doing for
what
the
I'm
bouncing
doing
ball.
the ball was moving around. It was sending over a method parameter that I'm moving the ball X and Y to X and Y, and the simulation would see that. So you can send over some data. But generally, I focus on behavior and then a little bit of data that's connected. And what's great about it, and I didn't show, I didn't really, I kind of be able to draw this, is that, so when you think about what happens with event streams or messaging system, is a call comes in, it collects data as it's going down the call tree and execution, and then at the end, someone packs it all up and sends it into a message queue. And it's got all of these fields which are kind of being collected. But what the simulation, our simulation does is that as you go down the stack, the data at the stack level is sent over that needs to be there. So at the end, if I'm only doing one parameter in that method that's at the end of the depth or stack, I can send that over, but the other data is already there present. That's up at the higher of the stack. So if you have systems where they go into a loop and then occasionally they change that behavior, then only that data change is replicated over the other machine. I don't have to replicate the whole method because there's a kind of a statefulness in the memory system or in the simulation.
Right. Wow. Thanks, William. Thank you.